In this video, we're going to review the BB84 protocol that you've already seen, but we're going to present it in a slightly different way using entanglement. This is called a purified form of the BB84 protocol. And even though at first it's going to appear like we're maybe making things a little bit more complicated, in fact, we'll end up giving more power to the eavesdropper. But this new purified form of the protocol will turn out to be much more convenient to analyze. So let's first look back at the BB84 protocol. So here's a summary of the protocol looks like. You have Alice and Bob interacting. The step that we're going to focus on is the first step of the protocol, which dictates that Alice should prepare BB84 states in random bases indicated by the string theta and send those BB84 states over to Bob. So she prepares states xj encoded in the basis theta j and sends that to Bob, where, just to recall, the four BB84 states are the 0 and 1 states in the computational basis and the plus and minus states in the Hadamard basis. And then there's the whole remainder of the protocol. So Bob declares that he has successfully received the states. He makes his own choice of a random basis, theta b, performs measurements of the states that he received in that basis, records some outcomes x. Then Alice and Bob exchange information about their choice of basis. They discard the rounds when the bases were different. Then among the remaining rounds, they choose n of these to be test rounds. In the test rounds, they check that the outcomes that they obtained were the same. They then discard those test rounds and they perform the post-processing steps of the protocol, information reconciliation and privacy amplification that you learned about in previous weeks. So now the modification that we're going to make to the protocol, it was suggested by a different protocol for doing key distribution proposed by Eckert in '91. So this is Arthur Eckert here, and I copied for you the title and the abstract of his '91 paper, and you can pause and read this abstract if you'd like. What's important for us is that it mentions Bell's theorem that we saw. And Bell's theorem is all about checking non-local correlations and verifying entanglement. So Eckert had a very powerful intuition when he introduced his protocol, which is that the non-local correlations that entanglement can be generated, these can be used as a means to verify that a particular state is entangled between Alice and Bob, and relying on monogamy of correlations that this state is not entangled with the eavesdropper's information, and this way guarantee you security. So we're not going to go into Eckert's protocol, we're going to stick with the BB84 protocol, but I wanted to mention his contribution because it serves as inspiration for the purified form of BB84 that I'm going to mention now. So what is this purified form? We're going to get there into two steps. So let's start from the original BB84 protocol, but modify it in a couple of ways. So the first modification that we're going to make is going to appear relatively benign. What we'll say is that instead of Alice preparing BB84 states directly, she'll do it in two steps. The first thing that she'll do is that she'll prepare EPR pairs, as many as she wanted to get BB84 states. So recall that this EPR pair 5+ is equal to 1 by root 2, 0, 0, plus 1 by root 2, 1, 1. So she prepares many EPR pairs, and for each EPR pair she keeps one of the qubits and sends the other qubit to Bob. So the second qubit here gets sent to Bob over the public quantum communication channel. Once this is done, Alice and Bob each independently make a choice of random basis and measure their qubit in that basis, recording outcomes XA and XB. Now I claim that this is equivalent. Why is it equivalent? Well, Alice and Bob can make their measurements simultaneously or one after the other. It shouldn't matter because they're in different distinct locations. Let's have Alice go first. So if Alice chooses a basis theta j and measures her share of the entangled state phi+ in the basis theta j, recording an outcome xj, what is the post-measurement state at Bob's side? Well, we know how to compute this. We simply have to project the first qubit in xj encoded in basis theta j, perform the identity on Bob's qubit, we apply this to phi+. What do we get? Well, because this is an EPR state, Bob's qubit gets projected into exactly this same state that Alice has obtained. So this is equal to xj encoded in the θj basis, but on Bob's side. And this is exactly the BB84 state that Alice would have sent over to Bob. So here the only thing we're saying is that instead of choosing at random a basis and an outcome, preparing the corresponding BB84 state and sending it to Bob, what you can do is prepare an EPR state, send half to Bob, measure your half in a random choice of basis, you'll get a random outcome and the corresponding state will be prepared at Bob's side. So this is exactly equivalent protocol. It's the first modification that I wanted to make. Now the second modification is going to appear a little bit less benign. What we're going to do now is give seemingly absurd power to the adversary. So let's bring Eve in to this picture, and let's assume that instead of Alice preparing the EPR states, Eve prepares them. So I'll just say that Eve gets to prepare an arbitrary state, ABE, shared between herself, Alice and Bob. She keeps the E system, she sends the A system to Alice, and the B system to Bob. This A system is supposed to be made of B of n qubits, and ideally Eve would have prepared this state into a tensor product of n copies of phi plus on A and B, tensored maybe some side information, but that is uncorrelated, that she'd want to keep. Of course, we don't know that this is the case, and in this protocol I'm allowing Eve to prepare any kind of state Ho ABE. Might be in this form, might not be. Alright, that's the first step of the protocol. The remainder is exactly the same. Now, let's imagine that Alice and Bob had a way to test that the states that are sent to them by Eve are EPR pairs, meaning that they would somehow implement the projection on phi plus on the shares of Ho that were sent over to them by Eve. In that case, the protocol as described here would be exactly the same as the one I described to you on the previous slide, which was exactly the same as BB84. So this would be exactly the same as BB84. Now I'm giving more power to the eavesdropper. Is there any reason to hope that this protocol can be secure? Well, let me give you the intuition why. Let's imagine that we modify again this protocol a little bit. The start is the same. Eve has prepared this state ABE. She keeps one system, sends one to Alice, one to Bob. This state is a priori, and I'd like to test it. So let's modify the testing phase. Remember, the testing phase was meant to look at a subset of the rounds in which Alice and Bob made the same basis choice and check that the outcomes were the same in those rounds. Let's modify this. Let's separate it into two parts, A and B. In the A part, Alice and Bob will project their systems, AN, BN, using the following projector, pi, AB, n times, will be the projection on the state phi plus. This is going to be a rank 2 projector plus a state, let me just call it phi A for that part of the protocol, n copies, where phi A is the state 1 by root 2, 0, 1 plus 1, 0. All right? And part B of the protocol is they do the same thing, but now they use another projector, let me call it pi tilde, AB tensor n, which is the projection on phi plus phi B, another state phi B, which is another of the Bell states, where now phi B is equal to 1 by root 2, 0, 0, minus 1, 1. Okay, let's imagine we could do this. Part A of the test projects on the rank 2 projector, whose span image is spanned by phi plus and phi A. Second step, phi plus and phi B. Now you can check phi A and phi B are orthogonal. So if a state passes both tests, then it must be a state that's phi plus. So these two tests together, they check that the state given to Alice and Bob by Eve has the correct form. And so if we have a way to implement these tests, we're in good shape, at least. The protocols were equivalent. So, but of course, it looks like this test cannot be implemented because you need to measure A and B systems at the same time, and Alice only has A, Bob only has B. What we're going to see in the next video is that in fact this test is equivalent to the test that's performed in the BB84 protocol. Meaning performing this measurement, this is equivalent to checking agreement in the computational basis, and the second test is equivalent to checking agreement in the Hadamard basis. So once we've seen this, we'll have shown equivalence of the purified form of the protocol to the non-purified form of the protocol. And then we'll prove security in following modules of the purified form of the protocol.